Today, I'm diving into one of the most mind-bending questions in cosmology. What is the universe expanding into? To get started, let's roll back to the early 20th century. Astronomers like Vesto Slipher and Edwin Hubble made some groundbreaking observations. They noticed that light from distant galaxies was redshifted, meaning these galaxies were moving away from us. This was a huge deal because it flipped the idea of a static universe on its head. Enter the revolutionary concept, the expanding universe. But what does it mean for the universe to expand? This expansion isn't like an object moving through space. Instead, it's space itself growing. To make sense of this, let's dive into some analogies. Picture the universe as an inflating balloon with coins glued to its surface. As the balloon inflates, the coins, representing galaxies, move apart. The farther apart these coins are, the faster they seem to move. This gives us a glimpse into how space itself is expanding. But wait, there's more. A more accurate analogy is a loaf of raisin bread dough. As the dough rises, the raisins, representing galaxies, spread out. This happens in 3 dimensions and doesn't need an external force, unlike our balloon. However, both analogies fall short in one major way. They suggest that the universe expands into something else, like air around the balloon or the kitchen around the dough. In reality, our universe isn't expanding into anything. It's expanding into itself. Our observable universe is just a slice of a potentially infinite cosmos. Over time, light from more distant regions reaches us, expanding our observable horizon. If the universe is infinite, it's always been infinite. Its expansion just means the density of matter and energy decreases over time. And what about the multiverse theory? Some suggest our universe is just one of many, born from a process called inflation. But even then, our universe isn't expanding into a multiverse. It's crucial to understand the universe as the entirety of space and time itself. It's about the fabric of space-time stretching and evolving. Let's take our curiosity one step further. What lies beyond the ever-expanding boundaries of our universe? To explore this enigma, we need to venture into some of the most fascinating and mind-bending ideas that scientists and philosophers have proposed. First up is the concept of the multiverse. According to the multiverse theory, our universe might be just one bubble in a vast cosmic foam. But what separates these universes? The answer might lie in higher dimensions, far beyond our 3-dimensional understanding. Next, consider the idea of an infinite void. Some scientists propose that beyond the observable universe lies an endless expanse of nothingness. What would it mean for our universe to border on such a void? Could it influence the way our universe expands and evolves? Another possibility is that the boundaries we perceive are merely an illusion. In a holographic universe, everything we experience in 3 dimensions could be encoded on a 2-dimensional surface. If this is true, the edge of the universe isn't a physical boundary, but a limit to our perception and understanding. And what about the idea of a cyclic universe? Some theories propose that our universe goes through endless cycles of expansion and contraction. In this scenario, the Big Bang wasn't the beginning, but just one of many rebirths in an eternal cosmic dance. Could the edge of our expanding universe be a prelude to a future collapse and another Big Bang? Finally, let's touch on the philosophical implications. What if the boundaries of our universe are simply beyond human comprehension? Throughout history, our understanding of the cosmos has evolved dramatically. From a geocentric model to an expanding universe, each leap has challenged our perception of reality. Now let's focus on one of the most enigmatic concepts in cosmology, the singularity. A singularity is a point in space-time where density becomes infinite, and the laws of physics as we know them cease to apply. To understand singularities, we need to delve into the theoretical underpinnings laid out by Albert Einstein's general theory of relativity. According to this theory, massive objects warp the fabric of space-time, creating what we perceive as gravity. When a massive star collapses under its own gravity, it can form a black hole with a singularity at its core. But singularities aren't just confined to black holes. The Big Bang itself is thought to have originated from a singularity, a point of infinite density and temperature where our universe began its expansion. Mathematically, singularities are points where equations break down. In the equations of general relativity, these points yield infinite values, indicating a breakdown in our understanding of physics. This is why singularities are often referred to as gravitational singularities or space-time singularities. One of the most intriguing aspects of singularities is their implication for our understanding of the universe. If the Big Bang emerged from a singularity, what does that say about the initial conditions of our universe? Could there be other singularities out there, giving birth to new universes in a cosmic multiverse? Let's take an even deeper dive into the origins of everything. What existed before the universe? What was there before the Big Bang? Could our universe have originated from such a multiverse, a bubble birthed from an endless sea of possibilities? Next, there's the idea of a cyclical universe. In this scenario, the Big Bang wasn't a one-time event, but part of an eternal cycle of birth, death, and rebirth. Imagine a universe that expands, contracts, and then expands again in an endless loop. This theory suggests that before our current universe, there could have been countless others, each one paving the way for the next. What remnants of these past universes might still linger in our own? Another fascinating idea is the concept of a quantum vacuum. According to quantum mechanics, even what we perceive as empty space is teeming with energy and potential. Before the Big Bang, there might have been a quantum vacuum where fluctuations in this energy field gave rise to our universe. This quantum foam, full of potentiality, could be the primordial state from which everything emerged. And then there's the notion of a higher dimensional space. Some theories propose that our universe is a three-dimensional brain existing within a higher dimensional space. Before the Big Bang, our universe might have been a part of this higher dimensional realm, waiting to be born. Could interactions within this higher dimensional space have triggered the birth of our universe? Lastly, we must consider the philosophical implications. What if the question itself is beyond human comprehension? What existed before the universe? The truth is, we don't know for certain. As we delve deeper into the mysteries of the universe, let's take a moment to explore the grand structure that binds everything together: the cosmic web. Imagine a vast, intricate network of galaxies, clusters, and dark matter stretching across the cosmos like a colossal spider's web. This structure is not just random. The cosmic web is composed of filaments of dark matter and gas, forming the scaffolding upon which galaxies are built. These filaments intersect at nodes where galaxy clusters reside, creating dense regions of matter. The spaces between these filaments are vast voids, almost entirely empty, where matter is sparse. But how do we know this web exists? Scientists use powerful telescopes and computer simulations to map the distribution of galaxies and dark matter. One of the most significant tools in this endeavor is the Sloan Digital Sky Survey, which has provided a three-dimensional map of the universe, revealing the intricate patterns of the cosmic web. Understanding the cosmic web is crucial for comprehending the universe's evolution. It helps us trace the history of galaxy formation, the distribution of dark matter, and the influence of dark energy on the universe's expansion. The cosmic web also raises intriguing questions about the nature of gravity and the fundamental forces that shape our cosmos.